Well, thank you once again for joining us for the 10th time at our annual hackathon. Also very good to see that the energy in the room is probably about on the same level as yesterday. I know that not all of you, had the chance to get the optimal amount of sleep, but nevertheless, thanks for being here. So today we are joined by a stellar cast of judges. We have Pedro VP Product at Enscape. We have Lawrence Blau, professor at Pratt Institute. Andrew Human, software developer at Hypar, as well as Leland Jobson, senior software engineer at NVIDIA Omniverse. Emilia Hernandez, director of design computation at TVS Design. Tianming Yang, design technology leader at Bagot. And Betty Chan, senior computational designer at Sidewalk Labs. We are very, very glad to have you here.
All right. Okay. This is JP. This is the sign. All right. Well, we're gonna get started. Our product is called Beetle. Well, Beetle. It's a work in progress, but it'll make sense. BAE stands for the technology behind of what we're doing. It's at the heart of it. It stands for variational autoencoder. We'll get to that part. Can we go to the next one? Well, we'll present the team the problem and it'll be all very clear. So this was a very exciting project to work at. We have a very diverse background. We have structural engineers, architects, software developers, and all kinds of ideas kind of converging here. And you'll see it reflected in the work that we'll be presenting. But you know, the whole idea is to take a complex problem, a complex design problem, is an optimization problem of a certain structure that is parameterized, and it can be thousands of parameters. And the idea is to condense those dimensions into just 2 dimensions, which is called a latent space for those that are not familiar with this technology. That's the VAE technique, which is a machine learning technique. And the way this works is that you come in with all of this complexity, for example, with a bicycle, that is described by a multitude of parameters. You condense them into a latent space, and then you explode it back into the original dimensions that you had. And the optimization problem happens in minimizing the differences between the input and the output. So that's kind of the crux of how it works. And the way to use it, for example, in a more familiar problem to us as structural engineers, would be to have, we can represent the beam, a cantilever beam, in very complex ways, right? So something like this, but then you boil it down into a line and then you explode it back in that way. Just another way to look at it for more insight. So we built off from a research paper by Dr. Van Haven Mueller. And this is the problem I was showing earlier, right? It's a very complex optimization problem, but then it's boiled down into 2 dimensions, which is X and Y. And then in the vertical axis, you have a metric that does make sense in reality, which would be a performance metric. So you can be talking about optimizing weight, cost, and whatever you can think of, right? The idea is to really apply this to any problem that can be expressed as a parameterized problem. So with that, we took that on, that framework. Let's go. Next. And we built a couple problems of our own to really run through the whole process and make our own, adopt this methodology and put it in a framework that goes end to end, from a user providing ideally a grasshopper model with a tabulated collection of samples, which would be realizations of a model. And then at the end, come up with some visualization and then get some models that are of interest to you. With that first problem that you were seeing there, it's a very simple problem with columns located randomly under a carpet-looking roof. And we came up with two metrics for this problem. There's an architectural metric that has a trade-off with an engineering metric. Architecture would be, for those that know more in architecture world, is compactness. We can get more into that later if you want, but this is a way to express the quality in terms of architecture. And the engineering would be simple, which is economy, pounds per square foot. So with those two, and the model expressed with all those parameters, we boil it down into this latent space that you can navigate and then get out of it a collection of configurations. If we go to the next one, the other problem was a dragonfly facade. And if you were there for the pitching session, maybe you heard something about insects. We did incorporate insects. It's an amazing structure. It's 60 meters tall. Let's go. And it's about optimizing the diameter of the elements of the wing, right? So something very similar in terms that you can express it as parameters. This one is 600 parameters because it's the diameter of every single one of these elements. The other one is much less. And then we showed that one. Okay, that's fine. We did everything Grasshopper, but then we boiled it down into a web app that's still in development. And let's go. This one is in development still, but this is the workflow. And what we really did to the heart of it, the VAE, is to enable it to use a multitude of performance conditions, not just one, because the original authors just had one metric. And then in terms of getting from your exploded features back into a performance calculation, they were rerunning their model. So we implemented a neural network to make predictions of what that performance was going to be. So just to optimize it. And I think we can go to the end. The framework is laid out. It's still rough, like anything that comes out of these things. But the idea is to allow a user to look at models with comparable performance to provide their clients with a multitude of options and be able to produce those models with a few clicks and then go from there and leverage machine learning in new ways. Ta-da. Questions? Yes. Should we be sharing this? Or?
Sorry to make you run. Sorry to make you run back and forth. My question was, how compact is the tools that you've made? I presume that you made like a few Grasshopper nodes or something like that. So how compact and user friendly are they?
So we built the web interface as a prototype and to explore more user interactions. So right now we have some dimensionalities as an input. So the first input and weight, it does not affect the design options, but it does show the trade-off between the two performance metrics we can have. So you can see when it drags, it just changes the landscape, and we'll know like how trade-off it will be. And the second one, P1 and P2, they represent the probability of being performed good in your current and perform conditions. So P1 is like, for example, metrics for architectural metrics, and P2 is represents for the probability for the structural metrics. And Z1 and Z2, and right now it's a slider like to explore and the point position in this latent space. But in the future, we would like to have people to can like drag points like inside this latent space, and it will be correspond back to a design option that is shown on the left. So, but right now it's a slider, and it just show like the coordination, the coordinates in this space, and like each one of the coordination responds to a design option. So yeah, that's the user interaction.
If you get 0, that means, you know, the probability of anyone performing better than you is 0. That means you're at best. And if you're at 1, that means you're the worst, because the probability of anyone performing better than you is 1, right? But the idea is not to give you an optimized solution, but allowing you to explore a landscape of possibility, so that, and also because it's variational autoencoder, the whole space is regularized, it's sort of, you know, standardized normalized distribution. So as you traverse through this landscape, everything is sort of contiguous. So you can see the form kind of morphs continuously as you see the metrics correspond to that, the metrics landscape. So the idea is to help designers to build up intuition over time, as opposed to telling them, hey, this is the best solution, take this. But we want to educate people as well.
Answer your question. It's a bunch of different steps. We haven't incorporated it all into just one single component. That's kind of like our future work. So right now we have to do some stuff in Grasshopper, Python back in Grasshopper. So, but that's the goals. We just didn't get into that one day.
All right. Thanks so much, guys.
Hi. Yes, ShapeMaker. You didn't hear it wrong, because this is a collaboration between ShapeDiver and the Spacemaker folks. And do I have to advance? Is that what we're gonna do? And so I'm gonna spend a little bit of time doing a little thing here for Safe Harbor. We're gonna show a bunch of products. There's no promises about us delivering or productizing any of this stuff. Don't make any purchases. There's also gonna be sort of a larger envelope of what we're talking about here. So hold on to your seats, because it's going to be 10 minutes of this stuff. So we did some Spacemaker collaborations, both with ShapeDiver and with TestFit. What you're seeing right now is a Spacemaker environment with TestFit objects and ShapeDiver objects in the same environment, getting environmental analysis in real time. And we'll unfold how that happened. Just a little bit about what these two products are before we get into TestFit, which you'll see in 5 minutes. Spacemaker is a cloud-based analysis and design application for early stage design, but we're expanding, where you can position your project someplace on the planet. You can get context for what it is. You can get environmental data on it. You can do your designs in that environment to get impact statements about what your design decisions do for the performance of the building. ShapeDiver is
essentially a very simple way to run Grasshopper models in the cloud and plug them into other web applications like Spacemaker.
And so the thing that we accomplished was we took ShapeDiver applications, we plugged them in through the API that is emerging right now into generators, so that you can take sort of arbitrary black box data that's coming from ShapeDiver, generate it inside of the Spacemaker environment, get whatever analysis that definition delivers, and then layer on top of it whatever analysis you want to get out of Spacemaker. So a lot of shapes and spaces and all the rest. ShapeMaker, Spacemaker, all the things. But anyway, it's about sort of how do we start getting these different superpowers all together into the same environment. The team, there's sort of more names on here than is probably up here, because there's a lot of overlap also with this group down here, which we're going to talk about with TestFit. Really a wonderful collaboration from my point of view on people who had never met each other, getting together into a room and just making some awesome shit. A lot of what kind of tied this project together is a shared vision about what's important. Automation, amazing. There's usually no single right answer. It's important to be able to see options. Both products are sort of about that. Web services make everything more collaborative, and all these environments really need to be built around the idea of extensibility and customizability. And so we really looked at this and we thought, what would happen if you can take encapsulated logic and put it into a design environment so that you can share it with people, so you can get more of a collaborative environment for people to work together for sort of performance-based outcomes. And just talk a little bit about how that was put together.
Yeah, so we can build all of these nice web apps which cover a use case, and it has cool AI analysis in the background. But for our community and for anyone here to be able to use it, you have to be able to hack it, right? You have to be able to do this bespoke buildings that we do, and any web app is never going to cover all of that stuff, right? So we need to basically allow people to plug in whatever they want in the back and then display or run the bespoke analysis. So what Spacemaker comes with is the kind of a place in the world, a context, but also these AI and analysis engines that you can automatically run on this geometry. Then they plug in generators. So we basically built a generator, which is a connection to ShapeDiver to generate things. This test fit connection is another generator in that space. Then the way ShapeDiver works is that it runs Grasshopper scripts, which basically means that because you run Grasshopper scripts, you can run most things as long as you can connect to them. So what we've proven in our sample is a connection to Cortex, which is basically an AI that lives somewhere else. We ask it what size should these members have. It comes back to ShapeDiver. That information is fed into Spacemaker. So there's a lot of sending stuff all over the web and connecting different things. There's also obviously built-in analysis you can do in these Grasshopper scripts, like Kangaroo, for example, and other connections, for example, pollinations to run additional environmental analysis that don't exist in Spacemaker, or environmental analysis that you're interested in.
Yeah, absolutely. So just to confuse you even more with more names, more platforms. This is basically, if you don't know ShapeDiver, we all know Rhino and Grasshopper, probably. This is the desktop side of authoring your definition. And what we're looking at here, this is part of, although it might not show up in the videos and the visuals, we are actually generating the structure. This is then the sizing of the columns and the beams is actually calling into Cortex, or our AI machine learning model here at Core Studio, through some REST API calls, pushes basically the geometry, the length of beams loading up, gets the size back, and reports that visually in the 3D viewer. Because of ShapeDiver kind of appifying these Grasshopper definitions, we're all of a sudden able to run them on the cloud anywhere.
So once the Grasshopper definition is ready, we can upload it on the ShapeDiver platform and already get a preview of it, get the API keys and plug them into Spacemaker.
And so I think we'll just play ourselves out with a sort of slowed down video of what we're doing. How much time do we have left? Are we totally out? All right. So thank you. We'll do questions. You guys have already sort of seen this at high speed, but this is sort of the full workflow of all of these pieces, all these sort of glorious pieces of technology coming together in one environment for the purposes of analysis and getting data from your design workflows. I think we can take some questions just sort of as you are scintillated by the glorious demo.
Thank you.
Thank you.
So are the, oh, I've never been accused of being shy. So earlier in the video when we saw those parameters and the sliders on the side, so basically are those getting pulled from the Grasshopper definition? Okay, all right. So, and then you're essentially allowing the user to control them from here. The definition computes and then it gets the results back here. Got it, okay. It's pretty cool. And theoretically, so that's kind of that example. It would be kind of the same framework if you plugged in, like you said, a test fit solver or even another kind of solver. Okay, cool.
Yeah, and
yeah, okay, on the geometry that you actually get back. Got it.
And part of the point of this also is just, okay, part of the point of it also is that users don't necessarily even need to know where logic is coming from in order to sort of get the functionality. It's a little small in this view, but I also want to point out opportunities for personal branding that happen within the Spacemaker environment for other applications. If you want to surface the idea of where this comes from and who is responsible.
All right, hopefully this has the videos in it. All right, so we'll go through this slides pretty quick so we can show the demo. We're team schema test. We're from TestFit and Spacemaker. Again, safest of harbors. We're scared of lawyers. We come from large companies. Like, this is hard enough to collaborate as is. So no products, no features out of this, at least no promises. This is our team. We have a lot of smart engineers, a few product people. And yeah, it was a lot of fun working with everyone. Next one. So we basically looked at it as, what if you could get incredibly fast office layouts with analysis, all in one user experience. It doesn't happen right now, and so we wanted to kind of show that.
The marketability issue, I think, for a lot of the Spacemaker neural nets in the US is a problem. And for large corporations that are moving to Texas right now, they're actually ones building Class A office. It's the only market that I know of where new Class A office is being built. So we have a shot, I think, at getting daylighting analysis, microclimate analysis, wind analysis, things that corporations care about for their employees. They want their employees coming into the office. I know we're in the post-office world, but there are still, like Wells Fargo, they announced massive building in North Texas. So I see a shot at marketability for Spacemakers, neural nets with Office, and I also see a shot at marketability where we have instantaneous generation.
Cool. Next slide. So what is TestFit and Spacemaker? TestFit is automated design or feasibility design. It's written in C, so not C++, not C#, but just C. Our engineers are amazing. It's a desktop application, so it's super fast. It's real time. You get that instantaneous feedback that's really important with procedural algorithms. And Spacemaker.
And just to say again, for Spacemaker, the point here is that Spacemaker is different than that. And we aren't using that same code base, and we are going to play with anything else that comes along. And so just sort of as an example of, previously you saw something that was working entirely with services. This is working with a different tech stack.
Yeah, so very different on the spectrum of software development or software engineering, completely different products. So yeah, we can go into the live demo now.
Yeah, can I hijack the sharing? Yes. Cheers. Oh, host disable participant sharing. Yeah. Sure. Ask to start video maybe? Or no, something else. Make hosts. Oh, okay. Okay. Yeah, I'll give it back. Great. All right, can you see the screen now? Great. So now we're inside of Spacemaker in the design mode here, and let me just remove the zoom things. Oh, getting in the way. Okay. So let me just select this plot and select a generator, then choose the TestFit Office generator that we just talked about. And here it pops up running WebAssembly, connecting through our API. And we can change the parameter that they have exposed. And you can see that they're changing live. Yeah, and I can save them and jump over to, take a second. Let's see, yeah, and then generate another building over here with the other options and stuff like that. I've cheated a bit, and so the analysis takes like 30 seconds, and I didn't want to spend time on that. So here you can see our sun analysis being used on the buildings that we just created using the WebAssembly that's compiled from TestFit code. And here's the daylight analysis. Yeah, so it's super cool to see how responsive this is, running their code in our service. I guess that's a demo. Should I show anything more?
Simulations. Yeah. Yeah, okay. Okay, thanks.
So one of the benefits of TestFit is that you guys get like pro forma and metrics out of it. Do you guys incorporate this into this one?
We don't have any time to hook up the
Or is
the data output.
Mm-hmm.
We had another week.
Okay. Oh, all right. Thank you.
So should I stand? I'll stand over here. Hello? Hello, everyone. Good morning. So we asked a pretty simple question. What if you could, can you hear me? Yeah. Okay, cool. Yeah, so we asked a pretty simple question. What if you could visualize your thoughts, your ideas in 3 dimensions instantaneously? And so, yeah, like what if you could take your dreams for the future and translate them into reality, all starting with a conversation. So this is what we think could be a new paradigm for 3D modeling. And the impact this could have, 3D modeling is a very specialized skill. This could really open up and make design more accessible so that everyone could visualize their dreams for the future. I need to talk more into the mic. So, yeah, next slide. So we have these amazing, powerful technologies. Next slide. But there's also limitations to those technologies. Slide. And so I'll pass it off to Sergey.
Right. So what we decided to play around with is another diffusion model that recently came out that allows you to actually generate 3D meshes as the output. And so what you're looking at here is a little Rhino plugin that we wrote that allows you to call into that model. The model is running on the server, and we're able to interact with it through the interface of your favorite design software. And as you can see, you can ask it to draw you an airplane, and it will draw you this. But nevertheless, close enough, baby steps. So the way it works currently is that we have a Flask server that is the host for the model that's able to accept HTTP requests. And the first prototype that we put together was actually in Grasshopper. I'm going to skip over this slide because I think you handed the microphone to me a little early, but that's okay. So we'll come back. And I can play this video. Great. So can we move forward? Okay. So we have a server that's serving the model. And because the inference time actually takes a little bit longer than HTTP requests would allow us to deal with, we actually have a Redis cache. So the way it works is, the client application submits a request like, hey, draw me a plane. And then the server spins up an asynchronous process and tries to draw a plane for some amount of time. And we have a separate route that the client can ping and say, hey, is it ready yet? Is it ready yet? Is it ready yet? When it's ready, it will be saved in the Redis cache, fetched from there and returned to the client so that you could look at something like this. And yeah, there's some of the outcomes of you know, it's just very it's poetic interpretation of your design process.
Is it? Yeah, you keep going. So we're really on the front end of this technology. And you can go to the next slide. But if we look back a little bit, this is where we were, this is where we are now. And so our blobs. So this is what's really exciting. We've built this framework to enable us to do this. And so looking forward, what could this mean for the future? We're here today. What could it look like in the future? Next slide. This video. The sound doesn't play, I'll just narrate over. So how do you design? Do you design with a pencil? Do you design with a mouse? What if you could design with your thoughts, your words, a conversation with a computer, a dialogue back and forth between talking? And so in this video, saying, okay, generate a building in the style of Dali. What if we push it out, extrude some panels over, rotate around the building, generate some structure, zoom in, and done. And yeah, this is the dream team, the amazing team. There is one more thing.
So we have the chance as well just to team up with the guys from Sainer, and they were really helpful. And we just tested some of these geometries that we generated through AI to populate them with chairs, because why not? How to build them in the office right next to where we're sitting. Yeah, that's pretty much for fun, but it was really good. Thank you very much for helping us with that. Yeah, that's the repo. If you want to have a look at it, it's all open source, and go for it. Thank you.
Do you guys have any questions?
The ML model that you're running, are you getting polygon meshes directly out of that? Are you having to do any sort of like ISO surfacing? Like, what is the data format that comes out of the diffusion model?
Technical question. Is it one model that's good for like all scales and applications, or is there like an industrial design object model and then a space model, et cetera?
Do you guys, hey, do you guys also see the seeds of where those geometries are generated? For example, those images that you have asked it to create, did it just create the model, or did it come from a seed image?
So you could use an image. This is going to be our beta release. Yeah, but yeah, no, you could absolutely use it. We just use Erika.
So if you submit that gorgeous building design as your own, are there legal troubles to be expected? What's like the licensing of the model output? I know everybody's favorite question, right? I did too, that's why I'm asking.
Okay, so our big question here is how do we interact with the physical world and digital world better? And one of my favorite annotations in architectural drawings is verify and field. And there's a great book on it Erika just recently put out. But the admission there is you don't actually know what's going to happen. So please verify, and then there's some sort of procedural or set of steps you're supposed to follow afterward. A simple one might be find the center, measure off the center, and align things. So there's that interplay back and forth, which is right now pretty simple. And so computational directives is a larger idea here. How can we actually use solvers? How can we make the best decision from that solution set? Because you're separating from the theoretical model and you're in some other world there. In order to accomplish that, we've got three things that need to happen. You have to capture the world. You need to do some best fitting to figure out what and how the current situation is going to impact your design. You need to remap and make a decision based on that. There's some optimization in there. We see the remapping as you could plug in a lot of the cool tools and solution solvers we've seen over the last few days. And the next thing is you have to direct some action. So how do you actually fix it? So the tools we use for this, we brought a Connect with us. This is kind of a stand-in for like a total station is what we use in the field. We used Open3D, a library for doing iterative closest point. And that's sort of the fitting of point clouds together. We then used Grasshopper and Galapagos as sort of our solver. And then we used AR Foligram and the magic gumball that Brian for McNeil, sorry, I didn't say McNeil. McNeil worked on as well. Rhino, yep. You want to talk about this part?
Yeah, so the feedback loop here, as James mentioned, you've got a scan that you initiate and you've got a modeled part that you're trying to find where that position is in the point cloud. You also have the coordinate system aligned so you know where that modeled part is in the assembly. And so then you, using hops, we connected with the Open3D library that runs on a Flask server. That's an open source library. And then you're able to use their sort of ICP iterative closest point alignments algorithm as a series of subsets there to sort of tune that alignment. And then it returns you a transform so that you can use that then to sort of drive the directive deltas.
Then a feedback loop to then verify the results of that feedback.
So here you can see us bring in on the left the sort of scan and fitting it based on a found object we had recreated and sort of modeled based on just some objects in this in the room. And then we've on the right side the sort of best fit algorithm that we were iterating on in terms of using Grasshopper tools, Galapagos, James was talking about. To kind of do a quick spiral through the workflow, we figured out we just do a random stack of chairs. We'd scan them. We'd use iterative closest point, get everything working. And then we also developed some bodega style survey markers that we use to re-reference the point clouds. So you find the sphere, you can shoot another scan, you can then reorient them together. Results were quite good. So the sort of field tools were fork, racquetball, cardboard box, paper cube with QR codes on it. And you can sort of see the whole scene there working together. This is another view of that, looking at the iterative closest point, snapping those things really quite tight to the model. Nathan here streaming in from the Connect, the Grasshopper, locating those parts. Do you want to talk about Folio?
Yes. So we use the Iruko cube photogram to identify the physical object to match it with the virtual space, and using photogram to kind of identify where the current object should be and where it needs to be. I think yep.
One version of what those directives might look like. So here, very simple, we have 4 chairs, and the directive is from the parent chair, find the minimal amount of movement to square them up. So that's the kind of thing you could think of in the field. Like you get a general sense of what's happening, and you make the best decision on what to do that minimizes or maximizes or does something good for you.
Prototype deployment of our found object being oriented to its scan position in space. I had to do some distinction between the other objects, though they separate, and then that sort of orientation element directing the chair in terms of its movement to its final position was the green one.
Yep, and then so with that kind of transformation matrix that we got from the previous slide, it got translated, bring into hologram to view in AR to kind of direct you and communicate with you what the step needs to be done. Yep.
So to think about what's next for us is that the future is now. So we collaborated with Dreamhopper team and worked on a text-based chair tower configuration. Yep. Exactly. So a narration to field. And so.
Well, now I'm talking.
So as you can see from the end result, this is something that you would not be able to achieve without the stack of technology that we have put together. But we use the computational design tools and the feedback to get the tower that came from Dreamhopper into reality. Any questions?
So your hops connection is to some iterative closest point solver, and then you're also utilizing Galapagos in some way. I'm curious about like the role of the various kinds of optimization in this workflow, and specifically like what the genetic algorithm is doing versus what the iterative closest point is doing.
So the closest point is sort of setting up the problem, and then we just use Galapagos as a stand-in for some directive. With the chairs, we were kind of trying to think of what we could solve with the chairs, squaring them up, moving them around. So it's doing the sort of feedback and then just generating the directive and coming back. So that could be kind of anything. You could hot swap that for all sorts of interesting solvers and whatnot.
Like a near future application, right? And knowing Zainer's work and everything else, right? So is this the idea beyond the chair, right? For instance, ways of kind of, let's say, Gary's work 10, 15 years ago, right? Finding ways to get the optimum position of panels that still have some global joint that allows, right, a kind of near fit. Is that what you're thinking of?
For sure. Yes. I mean, we prefab things, so we have good representations digitally of the objects we make.
Right.
Then they get to the field and things can get
Everything's
very
wanky. Yeah.
I think the example we talked about was like you go into a bathroom in the floor and there's like the tiles are laid out nicely and then there's like some squib. Like, why is there the squib? If you like scanned it, laid them out, added a 64th, like you can tune the installations. I think in a more wholehearted way. The tiles being the prefab unit in that analogy.
Thank you.
When are we going to see this in the MoMA?
Well, Rob said we couldn't actually glue the chairs together or cut them, so. But it's on the way. All right. Yeah. That's guys, good. Right. Yep.
We can go ahead.
Awesome. Hi, everyone. I'm virtually joining you, so thank you for having me too. So we are a difference engine project. What we aimed with the team was to create a tool that able to easily visualize and interact with change and change trends in your BIM models over time. If you go to the next slide.
So what we're looking at now is basically the tools that already exist. You can get this straight out of BIM 360 right now. The problem with this is, one, it's pretty hard to read and understand, and two, it's a static point in time. The list on the left-hand side is basically just a giant list of everything that has changed from one published point to another, which becomes very unwieldy to work with if you're trying to do anything other than just fix a wall joint or some of the really basic issues that are in your model. There we go. So what we wanted to do was understand who needed what information and when. And at the user level, the really fine-grained detail of making design decisions, making corrections in the model, and visualizing those changes across time, the highest level. Then we get to what the construction manager potentially needs. They don't care about that fine level of detail. They care about
quantity changes. They want to understand how the price is going to change based on those changes through time. And then when we get to the level of a QA QC manager, someone who wants to understand changes across multiple projects and how that's affecting their entire portfolio.
I think I got it. So we took multiple versions of a real project, generously provided by Matt, and we took so we built 10 files. I'm drawing 5 here. Working with Revit's quite slow, so Vim's got a free exporter. So what it does is it's an exporter from Revit, and it converts the BIM data into a form that's quite easy and fast to work with. It's got all of the BIM data and all of the geometry. So using the free exporter, he created multiple Vim files. And then we wrote a script. Well, I wrote a script using kind of a beta API we have with our desktop application. It's 160 lines of C# code. And what it did is it would compare the differences between each of the 2 Vims, and it would generate geometry differences and the delta represented as a JSON. So all of the changes, volume changes, movement, data changes, additions, and removals, so that we could visualize that using another format. So we processed about 100 megabytes of Vim data in 5 seconds to create about 200 megabytes of delta information that we then started to process. So off to Nick.
Hi, so we took the JSON files, thanks to Swiftlet for OBJ reading and JSON reading, passed them up into a series of charts and a 3D model, which we were able to stage with the delta information from the JSON file. All of this was eventually pushed up to the web with Sophie's help, thanks to Rhino as well, Rhino Compute. So our end result here was a web page. One more time. So just a quick demo of some of the sample models that we generated here. So it's very simple, colors change means that there's a different change to the object. Little mock-up of what we were aiming for. So our goal is to allow the user to see, graphical changes. It's a standard sort of dashboard approach, but we really want to allow the change step to be the thing that the user controls. So the 2 sliders across the bottom there can be as small or as wide as you like. You can look at changes from the beginning to the end, or just between the last two models that you have available. Next steps for us, we built this as a Revit sort of plugin because that was the test model we had, but our real goal is a sort of agnostic approach. Anything that can be turned into a JSON can be diffed. So it could be ETABS models, could be Rhino models, Tekla, many of these other things. The key is that we think that change happens, understanding it better is the goal of this tool. Just sort of theoretically, we were looking mostly in this session at one project, but our real goal is to be able to look at all the projects across the firm. So this is theoretically, bars across the bottom are a project. You have 50 projects. Where are the points that changes happen most? Is there some consistency there? Can we make better decisions in the future by knowing when things changed and why? Here's the team going hard at it last night. This is everybody that's up here with me now, as well as Tina online. Very diverse team, mixed backgrounds. We had a great time. Hope you enjoy the tool. Open source, of course. Grasshopper scripts are up here, as well as some of the code written by Chris for the JSON diffs.
Yeah, any questions? Any questions? Well, if there's no questions, Ben, why don't you tell us how you were going to use it?
So I represent a very small construction firm in the industry at Turner. We would use this as an opportunity. So like we set baseline budgets early on, and it's really hard because over time the design progresses, things get added, it's either owner driven, design driven, or even just construction driven. Things get added to the project over time. So it's really hard as you kind of work your way through all the different phases, and literally starting as early as concept, going all the way into CA and construction, and just knowing like where did we grow scope. So from our perspective, it's being able to just scroll through and see like where did steel get added, how much volume got added, and when, and what was the history behind it, so that we can figure out who has to pay for it at the end of the day. So really good use case. Yeah.
Is the format like not like 100% obviously, but is it like at least possibly agnostic to Revit? Could be used with other softwares as well.
Yeah, 100%. So the Vim format is BIM data without geometry or geometry. So we can convert like an FBX file or what have you into the geometric format, and we can still run the same diff tool. The JSON change sets are very simple. They're like for each element, what's the ID? Was it added, removed, changed, modified, and actually unchanged as well, so that we can actually properly visualize all of the data. And then for the geometry that we fed into the visualizer, we fed it as OBJs. So we just took geometries and went, oh, let's merge all of these. All of that merging, all of that processing, 5 seconds. I'm so proud of that.
So for the geometric diffing, is that actually happening? Like if I moved one vertex of some object, would it recognize that, or is it just here's a whole new mesh for the new version of this?
So it's only 160 lines of script. So what we're doing is we're simplifying and looking at bounding boxes, and there's a tolerance measure. So if you actually look at the code, you'll see I've got a volume tolerance and I've got a position tolerance. And we experimented with it to see, well, what is it? So right now we said, well, if it's an inch difference in the tolerance, we're saying, no, we're not even going to bother considering that as a volumetric change. But that's up to script. We could do a geometric comparison. That would take longer, obviously.
Yeah. Another question, I think as a coder, I rely on diffing all the time, to kind of keep track of change, but that works really well hand in hand with a process that also tracks the why of a particular change, things like commits, pull requests, things like that. Is there a thought about how you capture why above and beyond what changed?
Yes and no. There is a thought to kind of the value of that. How it would actually be captured is not really possible with the current tools, unless every time I move a wall, I require a user to say, I moved this wall because of X and Y reason, right? Which just to me didn't really make sense for usability. I think we had some very brief discussion around the why, but didn't really go anywhere.
We only have the model data. So unless the user's putting in their reasoning, we don't know. But maybe if you had enough of a landscape of changes, you could start to infer why those things are happening.
Yeah, I mean, it's time series data. So correlating 2 sets of time series data. So let's say you've got an issue tracking system, it's going to be time stamped as well, and then correlating the 2 of them. Because the whole thing is that seeing it in time, it provides additional information. You're like, whoa, there's a lot of churn here near the end of the project. Why is that? And that sparks a conversation. We even had conversations amongst us. It's like, why is this changing here? Like, what did they do to that floor that it deleted and then reappeared? And so those are conversations that even a design supervisor can have.
There was a good question also on the chat that I was also thinking about, that they said, what if you delete something and then recreate the same thing over again? Will it start detecting that? Okay. Okay. Understood.
To take it the next step further would be basically a replace. You could color code a replace. And so what would happen is the element ID changed, but everything else about it, all the characteristics and the geometry stayed the same. And then we could have represented that with a different color. So I think it's a natural extension. And then they can choose to view it or not view it. It's up to them.
Thank you.
Thanks so much.
Okay, hey everyone. We are a team of 5 people from, can you hear me? We're a team of 5 people from a few different firms. And the problem we've been looking at is how to manage scripts and workflows when working on complex multi-year projects. And there are really two main pinch points that we're looking at. The first one is the issue of massive Grasshopper scripts. And the second one is the issue of multiple people working in parallel on the same Grasshopper scripts.
Yes, so basically with the arrival of hops, there is a promise that we can do it better, right? We can finally do async calls, we can send it to other people to do it, we can build bigger workflows. But yet again, we'll still have a problem where you can have hundreds of hops components, and if you give them to people, it's very difficult to track what's happening, who's doing what, and why, right? So, of course, we are not the first industry which is trying to solve it. DevOps is here; it's been here for around, and people are using it. So, DevOps has a lot of tools and methodologies. One of them are Kanban boards. It's such an obvious way of tracking your work, right? Where you unitize a piece of code or a function, and then you track it. You assign it an ID and track what's happening over time. So our idea is to merge hops with DevOps to create DevHops, right?
So you can imagine this working on this sort of project, and this is an example where you can see that this is not just a tool, but also a methodology, and the two kind of have to work together. And the tool is really meant to make that methodology easier. And so this is a typical example where you start with an activity like massing, move on to panelization, and then have discrete tasks like patterning or creating a substructure or any of the other tasks that might be involved in that. And you have to manage that work among a group of different people.
Okay, so for the demo, I'll just move to YouTube. Okay, so that's the demo of our product. So basically on the left-hand side, just a second here. On the left-hand side, you can see two Grasshopper scripts. The top one is a master script, and this is direct sort of representation of the Kanban board. So each task is each hops definition. It has its own status. And the script on the lower left corner, this is the actual hops. So that's what's happening inside of this function, inside of this task. Okay, so so for example, you can see that we have thanks to REST Hopper, what you will see in a second, I have those different tasks that groups into groups. Yes. And for example, the coloring is direct sort of response from the Kanban board about the status. So if the task is in change requested or in progress, it will be orange. So let's say I was a reviewer of the script, I might want to request some sort of changes. So I want to put a task from in progress to change requested because I don't like the result. So now look at the Kanban board. Once I send the request, it directly moves the task from in progress to change requested. Then as a person who works on the script, I can directly read that, okay, for this task, I need to, I have some changes that I requested, so I need to fix my definition. Once it's fixed, I can post again the results that now it's up for review, and this is done. And if you look at the board, once I send it, the task should move from change requested to in review. So let's look at the board, fourth column. Yes, it moved. Wow. Okay. Okay, so now as a reviewer, I can come back to my master script. I can see there are changes. If I'm happy with those, I can either approve them in the master script or I can do it directly from the Kanban board. So that's what I'm doing in this example. So just write the message, all good. I can just drag to down the column and this all. So both the tools, they talk to our own API, but more about tech in the next slide.
At the end of the day, the five of us all contributed something a little bit different from our own backgrounds to the project. Technically, what we're looking at is a .NET 6 basic server with a database that allows both the front end and the Grasshopper plugin to communicate to each other live. Both of the clients are polling the back end as they push and make their changes, and as someone works with either the master scripts or is acting as one of the workers working on one of the subscripts inside the hops definitions. This is all available on our repo, all dressed up nice and available to take a look at. all the different contributions, including the Grasshopper script with some of the most intense care and attention to neatness I've seen in a long time. All available today with a QR code, so you can actually download it right now. This is us proving that we are all, oh, did you see it? Oh, yeah, this is what we want to look forward to in the future. Things that you could imagine could happen within the next hour or so, if only we had the time. Is testing after changes happen, or of course, using this history to actually show it in some way as things changed over time, and so on and so forth. This is us proving that we had a great time together, really love each other. And of course, no project about project management and Kanban boards would be complete without our own Kanban board. Thank you for laughing at the closing joke. Thank you.
Any questions?
Oh,
I thought so.
no, you are.
Testing.
Yeah, okay, so my thought, because basically what we are getting in the master script is the list of task IDs and all information about the tasks. So basically we know which IDs associated with which hops component. So I would just say for the testing part, instantiate all of the scripts and have hard-coded inputs, expect the outputs. If it's passed, we already have like the values in JSON that we pass, and right now all of our tasks, they pass the test because there's no test. But in the future, I would say that's like the simplest 1.5 hour solution.
If one aspect of this could make its way into Grasshopper as a first-class like environment feature, what would that be?
I think one of the things we had a lot of fun with that only got featured very briefly at the start was the like colors in the script as changes are happening. Maybe not use a group, but some way to like associate as changes are happening to the person as they're working. Right now, that's just like a basic status, but it could be the comments we were outputting or like exactly where things are wrong.
Because of the limited time, of course, we have it like group color, but if we can like hack the whole hops component and basically change the color of the actual component and link it directly, that would be the ideal like first step.
Yeah, at the end of the day, I don't see any reason why there's not a work item connected with the hops component from the beginning. So yeah, should just be part of it, I think.
Thank you.
Let's go for it then. Hello and welcome everyone. My name is Callum and this is my team. We are Team Crash and we've been working on a kind of multi-user Rhino. You may remember that I started off with some little bits of paper as I presented, but I have upgraded my collaboration skills and I think you should too. There we go, got a Crash here. So I don't know if you have these kind of problems where you have these pretty big models and you have one person who's basically siloed inside of it. And if they have any problems, if they can't make their deadlines or anything, you have to start splitting models up and it becomes quite a pain. Anyway, so why not Crash it? Do you know one? That works really well at the bar. Next one, yeah. I'll start doing finger guns or something. Okay, so the way it works is it's built on top of an SQLite database and a SignalR server that's inside of Rhino. You create yourself a shared model and you share that URL with other people. You can host that online or you can do that locally, and then everyone has access to that model essentially. Oh, sorry, yeah, cool. So, oh, I said I improved it, but honestly, I don't think this works quite as well. So poor old Bob has got his little deadline coming, but hopefully there's a solution. Someone wants to help. John wants to help Bob. That's very good, John. All right, but how can he do that? Yeah, nice. He's going to crash it. That's how he's going to do it. He's going to crash right into it. I just realized I haven't even explained why it's called crash. That's really important. In case you don't know, a group of rhinos is called a crash. I'm starting to realize that might have been more crucial than I thought. I thought that was fairly common knowledge. Okay. Sorry. So anyway, Bob can therefore create a little shared model on his local machine, which sets out the database permissions, starts a local server, and then John can join in. Everything sent back and forth between the two users. They crashed it. Perfect. But maybe we want a few more people to help as well. Excellent. We get the whole herd involved. All right. And the project is open source. And for many of us, certainly not the McNeil guys, but it's our first open source project. And that was really exciting. Working with a team of people who I've not really met before and not really worked before, 3 different companies coming together. 3? 4? 4. Wow, 4 different companies coming together just to create something cool together, this hackathon. Yeah, next one. Anyway, but now it's playtime. So we have created a server where you can go and play. You can go to Yak in Rhinoceros now, and you can download Crash version, say 1, and that URL is there. If you feed that in on typing in open shared model, put a name in and feed that URL, you can play with us. There we go. We're getting into the demo. I hope it crashes. The thing is, I feel like naming it Crash means we're not over-promising anything, right? It's true to its name. It's what it said on the tin. Do I have to do some stand-up whilst this is going? I might pass this off. Is anyone? Yeah, go for it.
All right. So we have here 2 Rhino instances running. On the left side, I already subscribed and started the server. On the left side, I can quickly show you. You can just open up the package manager, and you can see right now it's installed. When it loads, we have crash here. So I open the shared model. I type in I love New York. That's my new name. And I subscribe to the server, and there I am. So now I can like start drawing into the pipeline, and hopefully, nothing appears. So probably crashed. Let's see. We have here Cortes, Morteza, and Moustafa at least that came into the model. Let's see what they're drawing. It looks like on my left side, the subscription doesn't work anymore. Are you guys drawing something? Yeah. Do you see? Okay. It seems like for everybody else, it's, I am just zoomed out all the way. So let's see what they're doing. We have here our users. Everybody is working on it. We can add and modify things together. And once we are happy with our changes, we can release them, and they're getting baked into the Rhino model and released to everybody, basically. So yeah, it's a shame that I can't show this one here. Let's see if I actually can show it in real time working. It's really fast. So I would be sad if we can't do this. Let's see. No, that instance doesn't want to work. No. Otherwise, I would see the names here on the left. I think that one just crashed. But I can technically open up another Rhino instance if I have another minute.
If someone could open an issue report for units on our pull request, on our repo, that'd be really appreciated. Seems like units are a bit of an issue there.
All right, let's see. Go back in. We open the shared model, sign up as Lukas, and paste in the URL. No, it should be in there.
Wow. Please initiate a grasshopper command. Anything in particular? There we go. Everything's going, right? Just do it. Oh, sorry. Tough crowd, honestly. All right, you better do it, man. There's going to be threats. If we bake it in, it should. I mean, if you initiate Grasshopper, you're not going to see the theoretical Grasshopper stuff in other models because we'd have to talk to Grasshopper's pipeline, and we can't do that. If you bake from the Grasshopper script into your model, everyone else will see that. You have to click release. Well, you see it, you know, as sort of virtual. And then if you bake and release, then you get it.
And here we go. They're baked in.
So everyone gets a copy.
Everybody gets a copy.
Does that satisfy you? No, it gets locked.
I can only see it here in the different colors. Only when I release it, you can touch it and start.
Partial refund.
Yeah, exactly. I mean, this one here was released. This one here was released, so I can move it and then delete it again or whatever one I will do. And this user can do the same thing. Somebody just, you can see somebody, when I select it, it's gonna block it for me. So I can actually also not start editing it. When another user is occupying that element, I can't do anything with it until they unselect it. And here you go. Now I can also edit it again in the other Rhino.
Goku, when someone else moves something, is it deleted and recreated in a new place or actually moved? Well, Rhino events wise is deleted and then recreated in a new place. And so we do the same thing with this as well. It was much easier just to handle add and remove than every single Rhino command that anyone's ever thought of and in between. Partial refund, or is that good enough? Oh, that's time, sorry. But, okay.
Wonderful. Yeah, thank you so much, guys. Yeah, okay. All right. Thank you.
Yeah, exactly. So the server itself doesn't be trying to direct, just bringing JSON guide and come back. Good. Cool.
So, hi everyone. Great to be here. I have to say, great presentation, Crash team. It's amazing. I'm calling in from Toronto. I work at Woods Bagot office. And in this presentation, I wanted to look at visualization models. If you can go to the next slide, please. Yeah, so every, we have a lot of architects here in the background. Every team does visualization. They are great tools for a designer to convey their vision, to communicate the kind of experience they want to create. Great tools. And therefore, every project, every team spends time and energy developing visualization models, and then they develop these beautiful renders. So every project and team has this, but you know what every project does not have? It's an analytical model. So what I thought is, why not start using this model that we are certain that we are going to get for every project, and harvest it, and find design insight from it. So that's what this project is all about. So if we go to the next slide, please. So what you're looking at is, this is a radiance rendering that is done from one of the cameras set in the visualization model. So every visualization model is going to have cameras. So I started with that. So what you are looking at is the glare analysis. So what is glare? Very simply, glare is a very high contrast of ratio of luminance. Now, luminance is the light that is being reflected off of surfaces. So in this analysis, it basically predicts the percentage, the probability of glare that one may receive if they are looking at this view. And these colors are depicting, the potential sources of glare, and that's what the analysis represents. This analysis looks blacky right now because I have not really connected, the colors and the materials from Rhino, but that is something that I can optimize. So that's what the analysis is. Let's go to the next slide, please. Yeah, so the analysis has a prediction attached to it. Now we are looking at the interface for the app. This is a web app that is created using Streamlit. So you have, if you can press next, please. So you upload the Rhino geometry. Next, please. You select a layer to assign windows. Then you select layers that you want to ignore. You can also control glass transparency, and lastly, you decide how the sun is oriented to north vector. And once that's done, I'm using the Rhino 3DM library to connect a Rhino model into the Honeybee schema. And what you're looking at is the analytical model. So I have turned off the roof for the model, and this is how it is being converted. Next, please. And these are the queries that we are using to submit this model to pollination for simulation, and giving a feedback to the user how where the simulation is running. They can click on the link, go to the pollination, look at it. Next slide, please. Now, if you can please go to the next slides pretty quickly. So these are the outputs of this analysis. So all the cameras that were there in the model, they have turned into glare analysis. And this GIF, if we can, yeah. So this GIF really shows how the app works. Now I'm showing you the analytical model here in the web browser, and you can turn layers on and off. You can really explore this model, and yeah, it has the layers that you selected in the earlier prompts. They're there, and what it gives you is the series of images. And these are very rough renderings because I've used very basic primitive settings and radiance. But every image has this insight as to whether you are going to experience glare or not. So these are point-in-time glare analysis for all the cameras that were set in the model. So that is essentially the app. If we can go to the next slide, please. So yeah, so this was built using Ladybug Tools open source libraries. I used Rhino 3DM for the conversion. Then the app was built in Streamlit and packaged as a Docker container, and then it is deployed on pollination. Next slide, please. So yeah, these are some of the steps. The point I have chosen is, it's taken from a weather data. I have chosen the brightest day in a weather data, but there is a better way to decide when we want to do this analysis, and that is by doing another simulation, annual glare analysis. So that can be added, some more metrics. This is a very great way to create training set data because we are essentially tagging images. So this can be a good source to create a data set for machine learning model. And yeah, this is open source, hosted on GitHub.
How you guys doing? So we're config AR. Is controlling, whoops, okay. So we're optimizing the spaces you love. We have a diverse team of architects, engineers, and programmers coming from all different places in the world, from New York to India. Oh, okay. Okay. Our mission is to bring your parametric designs to AR. So we use reality capture, AR, and parametric design to visualize configurable designs in the real world. So the basic problem is that currently AR is a one-way solution. So AR solutions are divorced from field data. So that means that AR solutions are really difficult to scale and orient. And that means that as-built are very difficult to verify because they don't have this correct scale and orientation. The other problem is that AR is not interactive. So it's really difficult to evaluate design options interactively on site. And our solution is to bring parametric designs to AR in 3 easy steps. So you place your parametric design in the cloud. You use our app to capture field conditions. And then you can visualize those designs in real world generated from that field data. So basically, we're creating this 2-way connection between the field and the AR. So this is showing those steps. Very quickly here, you define in our app, you're defining a floor plate. Those points are then uploaded into the cloud. We're using ShapeDiver right now. And that is used in the Grasshopper script as an input. And it generates a model dynamically from those inputs and correctly positions it into your AR, which you can see through your phone.
Yes, and from a technical point of view here, if we look at the system, it's composed of 3 main components here. So we have the client application, which is a Unity iOS application. So that's the app you use to actually capture your points or your input data. And then we have this configure backend, which is essentially grabs this request and then it delegates that to Grasshopper workers. So we're using ShapeDiver for this demo, but the idea is you can obviously use your favorite Grasshopper backend, right? So yeah, this is kind of the Unity application. Kind of a zoom in here, you see the points being selected. And the interface here is really like those points, pass that over, you get back a GLB, which you can visualize in your phone in AR. And so looks silly, but this is kind of part of the innovation here. It's a pretty simple interface for posting these requests, right? So the idea is that you have your list of points that you get from your AR application, and then you also provide this model, which is a Grasshopper script. So, and the cool thing with that is that it doesn't have to be just one, layout office generator or whatever. It can actually be pretty much anything as long as you conform to this interface. You have those list of vertices, do whatever you want, and then you get a GLB back. So demo.
So here's the product demo. So going through identifying the floor plan and picking the points. I do want to mention that the whole idea here is it's right now we're working with points, but the idea here is that also we could in the future we'll do with different types of field data. So from here you can see we're generating a chandelier. Let's move to the next. And then here, we're just showing how this might work at different scales. So on the left, you have sort of another sort of decorative chandelier. In the middle, the idea is, what if this was on a site condition and you're looking at rebar? And then on the right, what if you're looking at an urban condition like a building and you want to see what your building might look like in an urban environment? So what's our future roadmap? As I mentioned before, we want to improve field data capture. Right now, it's just points, clicking on points, but that could be other kind of user inputs, measurements, area, and potentially also automatically get field data from object recognition and put that back into the Grasshopper model. And then the other thing we want to do is increase interactivity. So we didn't have time, but the idea was eventually as a dynamically generated UI, and you can actually in AR manipulate the parameters you have in your Grasshopper script and kind of play with it and see everything in real time. And obviously we want to improve rendering and visualization. So this very quickly is a example of what this might look like in the field, taking a look at rebar configurations and making sure it's properly implemented. And then here's a potential use case where, let's say you're looking at the interior of a room and you have a script for furniture layout. You press generate, and then hopefully in the future, you also add materiality and you can quickly see multiple different layouts for that room in AR. So.
Okay, just to wrap up, it's open source, of course, so feel free to clone the repos and play around. I mean, we think there is a pretty interesting innovation, just like the interface between, the accessibility of the AR applications and the power of Grasshopper scripts. So yeah, we had a lot of fun doing it, and hope you had fun as well. Thanks for us.
Okay, we can take one question. Or none, that's fine too. Yeah.
Does the end user have to configure anything on Unity, or they just download the app and just go ahead?
So currently, they can choose from the drop-down, and we have four or five different models in the Grasshopper. So they can choose from the drop-down with sending the same similar interaction, only with the points, and then it will return back the those. I think one of them is the office layout. One of them is the. You guys wanna also explain?
There's a rebar layout, and there's a chandelier. There's also, we saw a building in an urban environment. So
the concept is for this to be automatically generated. So you upload your scripts, you have your inputs, and one of those inputs would be, I want to collect area information from the field, and then use the app, and then you can press a button to change whatever inputs you defined in your output, so parameters you define in your Grasshopper scripts. All right, thank you.
Thank you so much.
Hello everyone. We are Project Vibe. We are comprised of, these are all of our team members. So we have a mixed skills of JavaScript on our team. Is this everyone can hear me? Okay, cool. So we're Project Vibe. We wanted to catch the vibe of a neighborhood in New York City. So the problem, so the problem is urban planners struggle to understand the business location information of their site. So when they have a new site, they need to understand what businesses are around here. So how do we properly contribute to the urban fabric? So when planning a new building, architects need to know what is the current vibes around their site. So our solution is Project Vibe allows users to query anywhere in New York City to find what businesses are in walking distance from their site, answering that common question, what's 5 minutes away from our site? So we joined together OpenStreetMaps and New York City Open Data and Mapbox. So one weird part, when we originally were using OSM, but OSM, as many of us know, has many different issues in the validity of its data. So that's why we joined it with a legally permitted data set created by Open New York. So one weird thing is that we found that to be a bingo game operator, it's called Game of Chance in the legally permitted data set. And when you join that together, many different institutions are categorized under Game of Chance, such as surprisingly churches, which is a little weird, since they hold raffles and bingos in the churches. And we also found cabarets and seafood as a categorization. So what we had to do in the next slide is we didn't want to have hundreds of different categories shown to the user. That's not really that useful. So we had to create a typology of entertainment, business, grocery, retail, parking, and these are the kind of typologies that you would want to know what is around my site when I'm trying to do that first day planning for a project. And I'll hand it off to.
Okay, so basically how this works is that users can enter a location point, and then you query an API, and then the coordinates for like the 5-minute walking distance will be mapped, and then you can visualize that on a map as well. And then all the business locations will be basically mapped out within that shape, within that polygon. And this is a demo.
So Project Vibe is available on desktop and on mobile. It's actually deployed now. So if you want to go to vibe.emptybox.io, you'll actually see it for yourselves. The part of it is works on mobile, not optimized for mobile user experience. But essentially what you can do, here we're going to actually Google this area. So we're going to type in the location. In this case, we're going to do the Equitable Life building at 120 Broadway. And we're going to submit just for a 5-minute walking distance walk shed. And if everything works, and maybe hopefully it doesn't crash, it works. So we can actually see all the business locations of that area created by typology in the bottom left-hand graph. So next we'll go over to Coney Island in Brooklyn. We'll do a 10-minute walk-in shed. And we'll fly on over to Coney Island. And you can see a very different building typologies around that given site. And so again, this is the data set from OSM combined with the legally permitted data set by New York City Open Data. So this was an effort just to try to solve that first day problem that architects have when they're having a new building project. And so this actually can be applied anywhere. There's many different APIs. There's Google APIs, which you can integrate with. You can actually use Here API, which is also traffic and place APIs. So if you plug in a different data set, this can be achieved anywhere. And these were all built, this entire project was built using open source technologies. So it can be applied anywhere. It allows you to quickly understand what's around my site on day one of a project or a competition. It can include other APIs and metrics. And yeah, it built from all open source technology and is available. Thank you.
Thanks so much, guys. I know we're over only by 50 minutes. We have 3 more teams to go through. So if you excuse me, I'll probably move on to the next team. But thank you so much, guys.
See, I'll be quick. It's a quick presentation here. But hi, I'm Chris Mackey, and I worked with Nick, 2 of us from Ladybug Tools, to make a sync model application. The main problem that we're trying to solve is not a very new problem, but it's an age-old collaboration problem that we've seen in the industry a lot. A lot of the times you have different people trying to work on different aspects of the analytical models that we use for energy modeling and daylight modeling. So you'll have a design team member who's working on the geometry, and they will pass that off to someone with more energy modeling expertise at some point, and they will start adding in metadata and properties and things like constructions and programs and all these things. And of course, while this is happening, the design team isn't simply just sitting and doing nothing, right? There's a new design iteration. And so there's always, a problem that we say is like the 2-week turnaround of trying to get the information back to the design team in a time frame that's relevant. And so what we are trying to do is trying to solve this by allowing basically the changes of geometry to be merged into energy models and vice versa before you get to the end of the design process here, right? Such that you can then get the timely information back to the relevant information at the time when it's needed. So we had previously a sort of rough command for doing this with our analytical models in honeybee and pollination. And previously, right, it was kind of in the dark. You just had to take another model. You didn't necessarily know what was in that model. It could tell you the changes, but we didn't necessarily know. You kind of had to trust what exactly those changes were. So in this hackathon, we used an open source framework called Streamlit, which is an open source Python package. And we used our open source core libraries in Ladybug Tools and our open source file formats to produce a web application that can give you much more control over this process. So the idea being here, this is the actual application that we built. So I have a model that I've built as an energy modeler that has lots of detail in it. It's clean. It has all this metadata for constructions and programs, schedules, and HVAC definitions, right? And so I was going to use this to inform the design team, but they just sent me this new model. They took my suggestion of making the windows a little bit smaller to conserve energy use. And so I'd really like to merge this geometry into my model where I've worked very hard on these schedules and metadata in order to give them the most relevant updated information. So we'll open up our application. We'll load our base model into that, right? The starting model that we want from that. I'll grab a file for the exported model with the most latest information that has all that geometry, but none of the metadata. And I will run a comparison report on that in order to give us an actual full diff of all the information in the model. So we're seeing just the rooms where the geometry has changed. I can see what's happening there. I can see if the geometry has changed and the energy property has changed. Of course, all those properties changed in this case because there was no energy information, I can say I just don't want to take any new information from the energy model in this case. And I can say, all right, maybe I'll just look at a few of the rooms here. Maybe I'll look at this entry hall and say, is this geometry make sense? Can I merge this in? Maybe I actually don't want to merge this in quite yet. I'll uncheck that from the geometry and I will merge that all together into a single model, which I can then open up, basically get a new updated model file with my energy properties, the geometry from the latest model, but just the geometry that I wanted from that checklist that you saw there previously, right? So this is that updated model with the, you can see with the smaller windows for most of the rooms, except for that one that I unchecked. And it has all of my nice energy modeling data here so that I can go and now give relevant design information, relevant feedback to the design team in a timely manner. Thank you. That's it.
Amazing. Thank you so much.
So we are graphics. Half of us are really obsessed with graph neural network. Half of us are obsessed with fixing stuff. That makes us graphics. Yeah. How do I go next? Yep, here is the team. A few of us here, we have remote people who helped us during the process. This is the problem that we are trying to solve. So what you see, this is the real model. On the left side, these are the models that comes, this one from Revit, a hospital building. All those gray area that you see shouldn't exist. This is on the right side is what needs to be. So you have to fix it. The current solutions are manual redrawing of the model. Takes days to weeks. This is what energy modelers, people who do like tailoring model do that, and they charge you for that. And then the other thing is to align the grid by users. This is the one that is available, take hours. It's currently available only in pollination cap plugins. And you can do it like this. So you just draw the lines and you say, oh, okay, these are the grids that I want things to basically align to. And it kind of takes it from 3 days to 30 to 60 minutes for every floor. So it's good, but it's not good enough. So what are the possible solutions to solve this? We started thinking, okay, what if we use graph neural network to teach the machine to find the problems and fix it for us? Or can we use any geometrical solution to find and fix these problems?
So when thinking about graph neural nets, you saw some great presentations when they talk about machine learning, but I just wanted to highlight that we see and use graphs more than we maybe understand. They are everywhere. So your Grasshopper script is like a graph. The floor plans that you deal with as an architect are also a graph. If you're a structural engineer, every model that you build in SAP is nothing but a series of nodes and some elements that are also a graph.
So in terms of preparing the data, we need to set up our own synthetic data. And we're using a generator to put the good data together, and then we intentionally destroy it, just so that we can have bad data. And then so that we can train with the bad data, looking for the ground truth.
So the most intuitive way of doing this is your graph is defined as nodes and vertices, I'm sorry, edges as edges. That's the most basic way. And it may sound intuitive, but there are some issues with it. For example, if you have 2 floor plans defined as boxes with 4 nodes, if one floor plan is intersecting the other one where there are no defined nodes there is no way for the graph to understand this intersection.
So instead of doing that, we're thinking of, okay, let's take each box as a node. And yes, that's us doing trying to draw the graph in our head, and using each room as a node, and then using the corners of each box as the attributes. So instead of calculating every single corner, so we're just calculating the relationships. That's insanely fast. It only takes us 20 seconds to generate 5,000 data, and I believe it's only take 5 minutes to train.
Yeah, so we started, if you have worked with machine learning, you kind of seen these kind of graphs. If the yellow one is spiky and crazy, it means you're not learning, you're just memorizing, and your model cannot learn well. But if it follows this kind of pattern, which is kind of regular, you have training, you have testing, this means there is actual learning. And it was very exciting for us. But unfortunately, at midnight, we were not getting this. We were getting garbage. But at 5 a.m., we kind of could get it to 85% accuracy. Back to Moustafa.
I told you they are just obsessed with graphs. Then we're just like, okay, this was good. Can we solve this with geometry after 5 a.m.? Because it didn't get us like 100% there. So what if we can just remove that part for guideline and find where the guidelines needs to be so we can just make it 5 minutes instead of 3 hours. So Google, have you done it already? We found a lot of projects. Integrate, yes, here, tried it, didn't work. This one, like a mesh fix thing, award winning, everything it does, amazing. Like I just read this, oh my God, someone has, of course. We sent this in, this is what we got. I mean, this is not a problem with mesh fix, right? Mesh fix needs the vertices to be joined. It wasn't, so it just didn't work. Then tried a few actually plugins, some people are inside this room, I don't name them, didn't work. Of course, we already tried the snap to grid, didn't work. Topologic beam, hey, have you solved this before? Didn't work. So we're just like, okay, what are we gonna do? So we took the original plan. We actually wrote an algorithm in Grasshopper for now, but it doesn't need Grasshopper or Rhino. What it does, it basically suggests based on a few parameters of like how accurate you want these things to be, and it weights these lines, and based on that, it fixes it. I know you can see all the differences between the two. No, you can't. So here's the thing. So this is the first one. Do you see this hallways down there? These things kills energy models. So this is what you get. We still have areas that we have to work on. That area on the top here is not resolved. Like now that's something to be solved. But this is already like saving hours and hours of work. And so conclusion, like everyone else, there is potential. Further development, we have to do more. So the things that we can do more is we can actually feed for this one. We didn't feed real world data, but we have a lot of real world data that we can feed to this algorithm to make it better. The other one, we already started to actually integrate the geometry one in Rhino and Revit and Web so everybody can use it. Thank you, get the source code here, and thank you to all these open source technologies, and some of them are not open source, and the internet.
Hi everybody, and we're a seismic simulation team. So our goal is to, we have three other people online. Matt, are you there? All right, so yeah, Matt is our, yeah, you can start.
Yeah, so we had a team, we were sort of split around the world. I'm in Los Angeles, there's a bunch of people in New York City, and then there's, we had people in Paris even. So it was kind of a 24-hour constant operation. You can go next.
So yeah, our goal is to visualize the seismic response of a 2D steel concentric brace frame structure under real seismic. So the streamline is to determine the load first, and then we use the CBF soil map developed by our TT Core Studio to get the frame design for each section. Then we use the ETABS to get the time history analysis results and export those geometry sections and displacement to CSV files read by the Unity. Then use the Unity to visualize the seismic response. So those are the TT in-house soil maps we developed. So benefit from those soil maps, we can design a structure in seconds. So we can see here, there's a wind node soil map. We can use that to determine the wind node along each direction. So we assume there are two CBFs along the y direction. So each frame will take about 23 K's wind node. So we input those parameters into the CBF soil map, then we can get the CBF sections in just seconds. And the right corner shows the L central curve we used in the time history analysis. Totally, there's 40 seconds duration, the peak acceleration is 220 gal. So that is the elastic analysis output for this time history analysis inside the ETABS. Yeah, we can play this video.
Yeah.
Unfortunately, we cannot hear any sound. So that is the Unity output to show to visualize this seismic response. Yeah, if we can hear the sound, that will be much more impressive. Sorry about that. Let's go to the next. Yeah, this is a detailed animation of the of some part of this frame. So Unity can change the camera. We can move the camera and get the very good animations here. Yeah, Matt, go ahead.
Yeah, so there's a QR code. It's up right now on itch.io if you want to play around with it works okay on mobile. The camera is more set up for a mouse. But basically we're taking in data from ETABS export as CSV. So there's no geometry being translated. It's just point coordinates and displacement numbers. And we're just importing that into Unity. It's all written in C#. It's up on a GitHub repo at the moment. You can go next. Yeah, so anyone that's familiar with Unity API, this stuff probably looks familiar. You can go to the next one.
So our team member from Paris used the Rhino to realize this animation under the Rhino and inside the Rhino. We can see that is pretty cool too. So in the future, we are going to model more elements into the Unity, like the wall elements, slab elements, and also we can show in some structure failure progression under the strong earthquake, realize the damage development across the whole structure dynamically. Okay, showcase the client how the structure is efficiently designed to resist the earthquake or strong wind using the performance-based design and Unity post-processing. And also we can use Unity to visualize the construction sequence. That can be our next goal in the next round of the hackathon. Thank you, everybody.
All right. So, well, all of this excitement is going on. We're happy that our jurors are back with us, and they're ready to announce the winners. Quick note before we actually get to find out who won this year. So the winners of the best overall hack, they get to pick the presents that are there on the table. Once again, thank you very much to Shimizu for providing the physical gifts for us. Thank you. And without further ado, let's see who won.
Sure. Well, because they get to pick. So, all right. Okay, so first of all, for best overall, we really appreciated just the fact how much the group was able to do in a short amount of time. Really appreciated kind of the elegance and simplicity of the tech that they used while also solving a super valuable problem. So thank you very much to the team of Crash for also giving us a valuable English lesson on the etymology and the meaning of the word crash. So congratulations, guys. Thank you very much.
Brief
but powerful.
Awesome. This is not my first hackathon, but I think it's my first hackathon where I've Sorry, I haven't been fed yet, and there's a lot of very good Chardonnay. So I'm going to do my best, and this little thing's going to do a lot of work. I think it's my first hackathon where I feel like a real programmer, and I've really enjoyed working with other real programmers. I guess it's such a weird bar, isn't it? I've really enjoyed it though. I've had an awesome time. New York is excellent. The bagels here are unbelievable, and I'm really going to miss them. All right, I'm fine. I can't believe the best hack. I'm sorry, wrapping up. Okay, someone else. Someone take this off me.
All right. So, I mean, just to echo Peter on this, like it was an incredible array of projects. We were all so impressed. There were more award-worthy projects than there were awards to hand out. So we're very impressed with the quality of the work and the level of effort and innovation and collaboration and all that good stuff. For the best collaborative hack, we would like to award the Remap team. We were super impressed with this hack on a lot of levels. It was, it was one of these things where looking at it, we felt like this was, the team was cross-disciplinary, and we felt like the product and the vision of how this could work is how construction can work and will work in the future. And it's great. We're very, very happy to award you this prize.
Oh, yeah.
Thank you.
Thank you.
Aww.
And the future is now, probably was our slogan there.
But yeah, I cannot underscore how difficult it was to pick any of these. There was such amazing work. For the best open source hack, we decided to choose the Dreamhopper team.
Do you guys have any comment? Because I don't. Dream on, dream on. Thank you, guys.
Thank you.
Hi, everyone. We have a surprise and also a late hi. I tried really hard to run over the marathon, but I couldn't, so I got late here. Sorry. So as everyone mentioned before, it's really hard to decide awards with a limited amount. So we squeezed really hard. We fought for an extra place for honorable mention for graphics. I hope they take this one this award, but oh, please welcome on stage. So I think so we believe you the incredible amount of research that you have done, and given the very extreme time constraint, you tried really hard to like get your theory out, and then at 5 a.m. you actually found a hack to make a way around, and then something that's incredible amount of effort into something that a small change have a great impact. And that's something a lot of tech companies are doing. So great job. Congrats.
Well, thank you so much. I'm not the core contribution behind this. There are many other impressive, amazing people. I'm coming from academia. I'm a professor at NJIT, and I'm really realized the importance of collaboration between academia and industry and the power of industry. It's amazing. So it was a great opportunity. This is the first time I attend this hackathon and also this conference. Coming from academic research area, I really want to enter into this real world implementation. Yeah. Thank you so much. Thank you.
Oh. So just one clarification. The prizes there, and in the spirit of democracy, there's 3 gifts that came all the way from Japan via Shimizu. There's a beautiful lantern. There's a bottle, beautiful bottle, as well as a bunch of cookies all the way from Japan. So each team gets to have one of those 3 things. So you can fight it over, but consider it all from Japan. And of course, the cash prizes from Amazon. So anyway, so just to first thank our esteemed jurors, old friends and new. Huh? Also, thank yourselves. Like, I mean, amazing amount of work and collaboration that went into these hackathons. This is probably our largest hackathon that we've ever done, which is amazing, actually, right? Really amazing. So big hand of applause for everyone, right? So the other thing, again, those many of you here who put together the workshops, you know, I feel like this hackathon in particular would not be the same thing if it wasn't for this buildup, this sort of crescendo of, you know, the workshops, learning new things. We had the symposium, amazing talks, the beers, and, you know, just chit-chatting. So much going on. We will promise to have more salad next year. That's the other thing. We had a lot of carbohydrates this year. But I think that's sort of what has been amazing, at least for me. And, you know, from a personal standpoint, and, you know, to see everyone get together, sort of, you know, not worry about what company you work with, what vendors you come from. I mean, we have Autodesk, we have ShapeDiver, we have Spacemaker, of course, McNeil. By the way, big hand of applause to McNeil as well, too. So, yeah, I don't know what else to say except for it's been amazing. It's been phenomenal. And we will definitely do more. You know, maybe a different city, maybe a different location, whatever. Just, you know, also give us feedback. We're always interested in getting feedback to sort of build upon the next year, the next event, whatever. And big hand of applause to Dave Mans, as well as Giselle Vargas back there.
And of course, a big thanks to Rob and all the TT team, right?
All right. That's it, folks. Have a great day and have some more beers, etc. See you.